Hello, in this tutorial we will learn how to use RapidMiner to partition a data set into clusters using the k-means algorithm. And we will examine the output from the clustering algorithm. There are various kinds of output that's given about the properties of the cluster, so we will examine that output, and we will end the tutorial with a discussion of how to determine a good value for the number of clusters, because that has to be specified up front. So a quick look at the data set that we are going to use. We have data on about 200 customers, and this is from a store. And for each customer, we have three pieces of information, three features: the age, the annual income in thousands of dollars, and a spending score that has been assigned to the customer by the store. Okay? And the objective is to divide off this set of customers into clusters. And the idea is that customers in one cluster will be more similar to one another and dissimilar to customers in other clusters. Okay, so that's been shown geometrically over here. The algorithm that we are using, the k-means algorithm, is very simple-minded. It starts off with k initial centroids. It assigns each customer to the closest centroid, and then the resulting k clusters that happen, you recompute what is the centroid of each of those k clusters, and then reassign each data point to the nearest cluster, and you keep doing this. So reassign, recompute centroids, reassign, recompute centroids, until the position of the centroids don't change at all or don't change a whole lot. And then of course at the end we will have a discussion on how to determine the number of clusters. Okay, so with that, let's start up RapidMiner and we can begin our model design process. So let me first bring in the data set, the mall customer data set, and I'll just temporarily connect it to the output so that we can take a look at it. I will run this very simple process, and you can see those variables, those features of each customer. But what I'm more interested in is the summary statistics, and I want to point out something here. So if you look at these three variables, age, annual income, and score, you can see the ranges of the values. So age ranges from 18 to 70, spending score from 1 to 99, and annual income from 15 to 137. Now in this particular example, these three variables, their values don't, the ranges are not wildly different, okay? But you can easily get data sets where the ranges of these quantitative variables are drastically and dramatically different. So you could have one variable that ranges from, let's say, 1 to 3. Another variable ranges from 10,000 to 50,000. A third variable ranges from 0 to 5 million. If you have situations like that, then when you're running a procedure like ours here, which is distance-based, the k-means algorithms is distance-based. After all, you're trying to cluster groups based on similarity, then this kind of disparity in magnitudes of the values can affect the clustering. So it helps to standardize the variables. So it's good practice to standardize the variables before you cluster. So let's get back to design, and I will disconnect this link. I first want to get rid of the customer ID, and then I will standardize. So let me quickly do that. So select attribute. I drop it into the process panel, connect the two operators together, go back to select attributes, go to the parameter panel, and then select customer ID, and tell RapidMiner to invert the selection. So it has just dropped customer ID as a variable. And now I can standardize or normalize. So here's I just typed in standard, and RapidMiner knows that I'm trying to normalize. So here I pop in the normalize operator. I connect it to the previous one, and I go back to normalize, and you can see on the right hand side that I'm telling RapidMiner to normalize all the variables, all the features of the customers. And there are a number of different ways to normalize. I'm picking the Z transformation. It's a very common way of normalizing. So each value minus the mean divided by the standard deviation. That's the Z score for each value. So just let me quickly just show you the results of that transformation. I'll just run this process. and you can see that for each quantitative variable now, each feature of the customer, you don't see the absolute values anymore, but just the standardized score. So this first customer, for example, is minus 1.4 standard deviations in age. So this is a really young customer. And you see customer number 11, age is 2 standard deviation above. So this is one of the older customers. Okay. So let's get back to design, and let me disconnect this link. I'm now in a position to bring in the cluster operator. So here's the clustering. There are a whole bunch of different clustering operators. We'll pick the k-means one. That's one of the simpler ones. So I drop it in here, and the operator says where's the data points to be clustered. So it wants the examples. So I connect the output of normalize to clustering, and now I'm in a position to actually do the clustering. So if I click on the clustering operator, so one of the important inputs to that process is how many clusters do I want. That has to be specified up front. And as I said, we'll have a discussion of what that should be. We'll have the discussion towards the end of this tutorial. For now, let me put k equal to 2 because that is the smallest value that I could have. If I'm trying to partition a data set, then at the least I need to partition it into 2 subsets to k is equal to 2. That also makes my discussion simpler, and then we can look at higher values of k later on. So here is, I've set up the parameters for clustering. Now I got to take my outputs and put them into the results port so that I can actually watch the output. Now both these 2 ports have the name CLU. That's a little bit unfortunate because they give slightly different kinds of output. Now this first one, when I put my cursor on it, you can see it actually gives the summary of the clusters. It will tell you, for example, where the centroids are, the number of data points in each cluster, and so forth. So that's what the first output port does. So let me connect it to results. And the second output port, when I put my cursor on it, you can see it shows the raw data, so data for each customer, but also which cluster they have been assigned to. Okay, so let me connect that to output as well. So here is my results output. So now I'm in a position to actually run the clustering process and look at the output. So let me run the process. So here you can see the the clustering, the output from one of the ports. So from one of those ports, you can see you have the 3 properties for each customer. And for each customer, you also know which cluster they were assigned to. So for example, customer 3 was assigned to cluster 1. But I'm more interested now for this tutorial to look at the cluster model, what its properties are, what is RapidMiner telling me about, what's the summary data about the clusters. So first thing it tells me is that I have divided off your 200 customers into 2 clusters. Excuse me. The first cluster has 97 items. The second cluster has 103 items. That's nice. We always want to have clusters that are reasonably balanced. If we end up getting highly unbalanced clusters, that's usually a source of concern. Now, the second tab over here is folder view. So we are actually now drilling down and getting more and more information about the clusters. So since we specified 2 clusters, these 2 folders tell you which customers are in each cluster. So if I click on any one folder, I get a list of all the customers who are in that particular cluster. If I click on any one customer, I get the summary in the properties of that customer. So this is a customer who has spent a lot. So is one of the higher spenders. You can see is 0.8 standard deviations above the mean. And this is one of the younger customers. It's minus 0.6. So it's 6.6 standard deviations below the mean. And this is also a customer who doesn't make a whole lot of money. So maybe they're spending money they don't have. I don't know. So it's minus 1.5 standard. So it's 1.5 standard deviations below the mean. Okay, so this is information about each customer in their respective folders. Now let's look at the graphical representation of the clustering process. So here you can see the root node is the original data set. It has been split up into 2 clusters. And if I put my cursor on any one of those clusters, I get summary information on it. So there are 97 items in that particular cluster. If I go on the second cluster, there are 103. Now, if I click on any one of these clusters, you can see on the right hand side again, this list of customers shows up. If I click on any one customer, I get summary information, the features or the properties of that particular customer. Okay, so now the next tab is the centroid table, and it gives us very useful information. So there are 3 features of each customer. So each cluster, the centroid of each cluster is determined by, is specified by values for those 3 attributes. Now, if you look at these 3 values, you can see that for age, the centroid of cluster 0 and the centroid of cluster 1 are very far apart, minus 0.75 and plus 0.707. So very nicely differentiated. Similarly, if I look at spending score, the centroid of cluster 0 and the centroid of cluster 1 are very well differentiated, plus 0.74 and minus 0.69. But in terms of annual income, the 2 centroids are not differentiated at all. They're almost at 0. Okay, so the second attribute is not, this annual income is not helping much in terms of separating the 2 clusters. Okay. We can see the same information graphically when I click on plot. So the blue line and the red line represent the 2 different clusters. I forget which is which, but that doesn't matter right now. So what this picture tells us, that in terms of the age feature, the 2 clusters are differentiated very well. So you can see the centroids are very widely different. Okay. Similarly, in terms of spending score, the 2 clusters are quite well differentiated. But in terms of annual income, the 2 centroids are pretty much identical. Okay, they're not differentiated at all. Okay, so this is the summary information that we have gotten about the 2 clusters. So let me show you the impact of changing the number of clusters. So I will just change the number of clusters to 3 and rerun the procedure. So here's I rerun the procedure. So let's get back to the cluster model. And what I wanted to show you is go back to the plot over here. And you can see very quickly, we can see something here, that now that we have gone from 2 to 3 clusters, look at what has happened to the centroids. So here we can see that in terms of age, the centroids for the 3 clusters are quite well differentiated now. Okay. Similarly, in terms of spending score, the centroids of these 3 clusters quite well differentiated. Okay, and if you remember, annual income was not helping in terms of separating the 2 clusters, but now that we have specified 3 clusters, you can see the centroids are quite different now. Okay, so annual income has helped in separating these clusters into the data set into 3 clusters. So the number of clusters does affect what happens and the quality of the clusters that you're getting. So, and now of course comes the question, so how should we determine what should be a value of k? What's a good value of k? I've shown you that the value of k affects the results of clustering pretty dramatically. Okay, so the one of the ways in which to determine k is by the nature of the application. So whatever application you're doing this clustering for, that can sometimes dictate what the value of k should be. For example, if you are United Airlines and you're trying to cluster your passengers into different categories, so let's say your business model is such that you have platinum members, you have gold members and silver members. That is, your business operations can only allow you to support 3 categories of customers. Then if you are clustering your customers, it makes sense to make k equal to 3. It doesn't make sense to have k equal to 5, k equal to 6, because your business processes are not going to support that. A similar example, if a professor, let's say in a calculus class that has 200 students, looks at the numerical scores at the end of the semester and wants to assign grades, so university policy, let's say, is to assign A, B, C, D, F. So A, B, C, D, F, 5 grades. In that case, the professor should use the number of clusters to be 5. It doesn't make sense to have 7 clusters when your grading scheme only allows for 5. Okay, so oftentimes it is the application for which you're doing clustering that will dictate how many clusters you should make. Okay, now if you're in a situation where the application provides absolutely zero guidance on how many clusters there should be, or if you're sort of basically ignorant about the context in which you're doing the clustering, then there are internal metrics that one can use. Remember, this k-means algorithm does its clustering based on distances, right? So we can stick in a performance metric that tells us that for each value of k, how is the clustering performing in terms of distances. So some distance metrics are provided to us, and based on those performance metrics, we can decide what is a good value and optimum value of k. So that is what I'm about to show you next. And for that purpose, I have to introduce a new operator which will tell us performance of the clustering as a function of k. So let me first retrieve that operator. So I just type in performance in the operator panel and I get a whole list of performance operators. So out of all those ones, I go to the performance operators that are specific to segmentation clustering. Okay, so you can see cluster count, cluster distance, cluster density. I will pick up the cluster distance performance operator, bring it in here and drop it into the process panel. So what's going to happen now is instead of taking my output from the clustering operator and directly just viewing it, I will feed this output into the performance operator, which will look at what the clustering procedure has done, tell me the performance metrics, and I will then run this over and over again for different values of k and decide what value of k I should choose. Okay, so now if you look at the performance operator, it has two inputs, CLU and EXA. So the CLU input, it wants the results of the clustering process. So it basically needs to know the centroids, the number of customers in each cluster and so forth. Okay, and you may recall that it's the first port from the clustering operator that provides that information. So that's what I will connect. Okay, and now the second port, this one, from the clustering operator, I connect the output port over here. All right, so this is another situation where the same name for these two ports is somewhat confusing, but it's something we have to live with. Okay, so the performance metric that comes out, we will see what those performance metrics are when we run the procedure, but as you might guess, they are distance-based metrics. So I will put this output over here. Okay, and I know I might want to look at the examples. I mean, each customer, which cluster they have been assigned to, as well as data on the clusters themselves. So all three outputs I'm putting out. I needn't look at all three, but I will, since I have them, I will just look at them. The main thing I want to focus on is the performance metric. So now that you look at this process, you can see what I have basically done. I've taken the original clustering process and I've just stuck a performance operator in at the end of it. And I've taken the output of clustering, feed it into the performance operator and look at the performance. So I will just run this process over and over again for different values of k, and from that I will choose what is a good value of k. So let me get back to the clustering operator and reset the number of clusters to 2. That's what we had originally, if you remember. And so we will run this procedure now, this process. So here we go. Okay, so these two tabs, so the example, this is the example of output from clustering for k equal to 2. So you can see the different customers, their feature attributes, and each cluster, what cluster they were assigned to. You've also seen the clustering model output. So 97 items in the first cluster, 103 items in the second. So this is what we have already seen. The new information that we got from our performance operator is here in this third tab, which says performance vector. Okay, and this is where the numbers that we get. So this is the numbers that I want to focus on. So we have two clusters, k is equal to 2 here, right, in this iteration. So it gives me three numbers. The first number, it says average within centroid distance. So it is telling me on average, that is across both clusters. If I look at both clusters together, on average, how far are the data points from the respective from the respective centroids. Okay, so and it says it's minus 1.19 is the metric that I've come up with, and it also gives me the average distance to the centroid for each cluster separately. Okay, so you can see that the average distance for the second cluster is minus 2.1. The average distance within the first cluster is minus 1.7. And this first average distance is simply the weighted average of those two. All right. So this is the one number I will focus on, this minus 1.1937. So what I'm hoping to do is to shrink this number to get the customers closer to the respective centroids by increasing the number of value of k. So let me go back to design, click on clustering again, change k to 3 and rerun the procedure and go back to the performance vector. Now do you see the within centroid distance has dropped a bit from 1.7 to 1.4. So I have gotten, by having 3 clusters instead of 2, I have gotten the data points closer to their respective centroids. Now, if you just think about it a bit, you can easily see that as I keep adding more and more clusters, the data points will get closer and closer to some centroids because there are more centroids that they can reach out to. So it's pretty obvious that increasing k, this average distance will monotonically decrease. Okay, so there will not be a natural maximum. So this will monotonically decrease. So the question is, where should I stop? When should I stop increasing the number of clusters? All right. Now, so this, if you get back to the design, so if I can keep changing the value of k, and for each value of k, I know I will get a lower and lower average distance. So where do I stop? So typically what happens is when you keep increasing the number of clusters, the average distance will keep dropping, but it will show an elbow, okay? And you try to stop at the elbow. I have taken the liberty of running this procedure for you for different values of k, and I've actually created a graph, and I have a data set for that. So let me just pull in that data set, okay? And I will connect it to a results port. So this is a completely independent data set that I have created by running this process many times for different values of k. Okay. All right. So let me run this process now. So when I run this process now, I'm not interested in what happens here. I'm interested in showing you the results of my prior analysis. So let me run this. So here is what I found. Okay, when I ran it many times. For k equal to 2, you already saw that the average within cluster distance was minus 1.9. So as we increase the value of k, this average distance keeps dropping. Do you see? But what does it actually look like? So in terms of graphical, so let's visualize it. So here's the graph. So you can see for different values of k, as k increases, your average distance, now this is negative c, so your average distance is going down. But do you see that there is an elbow in the graph? And that is typically what happens when you're doing clustering. After a point, you get very incremental improvement. And there is always a danger that if you increase k too high, it might seem like you're doing better in terms of average distance to the centroid, but you might be overfitting the data, okay? So when I just visually look at the pattern over here, it seems to me that beyond 6, okay, so even from 5 to 6, I see a good drop in terms of average distance, but 6 to 7, I don't see a whole lot, certainly not from 7 to 8 or from 8 to 9. So based on this inspection, my judgment is the elbow is at 6, and I would stop at 6. So I would use a value of k equal to 6. For my clustering. Now, so this is the approach I would use if there is nothing in the application domain that tells me what value of k to use. All right, so in this tutorial, I've shown you how to cluster data based on the k-means algorithm. And I've also shown you how to look at the performance metrics to decide on an optimal value of k when the application domain itself doesn't provide much guidance as to what the value of k should be. So thank you for watching and thank you for your attention.